what would happen if we put a topology onto a vector space? Or maybe even a better question, why would we want to put a topology on a vector space? I've got the vector space v equals r2 on the right here, and I've graphed the vector 2, 2. But what would be the benefit of having a topology on R2? What we really care about, what makes topologies so powerful, is that they are the basis of where we get continuity from. They are fundamental to have continuity. If you want to talk about transformations on a vector space being continuous, you need a topology. I'll give you, let's transform this vector 2, 2 on the right here in a continuous manner. I scaled the vector, I rotated it, but behind the scenes, that was all just scalar multiplication and vector addition, which leads us to the definition of a vector topology. Give me a vector space V, I'll give you a topology tau that we'll call a vector topology if tau satisfies 1, vector addition and scalar multiplication are continuous operations or transformations with respect to tau, and 2, for all x and v, the singleton set containing that vector is a closed set with respect to tau. And I made a little asterisk there because this isn't always included in the definition of a vector topology. For example, Wikipedia, their definition only includes 1 here. However, the benefit of having both of these is that it turns out 1 and 2 both are sufficient to show that your vector space V is Hausdorff. And when we give V this topology, then we call V a topological vector space. I'll give you 2 more illustrations. This is the vector space R3 now. And as we rotate this vector around, we're not really scaling it. Behind the scenes, this is really vector addition. Intuitively, this rotating movement should be called continuous. And indeed, if we have a vector topology, any vector topology on R3 would consider this movement continuous. Maybe more interesting, especially if you're trying to solve a differential equation or system of differential equations, is the example on the right, which we can consider as part of the vector space of functions, smooth functions of 2 variables, c infinity of R2. You can imagine this oscillating motion happening to, let's just say we start with a function z is equal to u of xy, and we multiply this by some scaling constant alpha. Here alpha is a real number, so we're scaling this function u up and down, and let's say it makes this function u, when we graph it, do something like this. This crazy looking number, this would be your alpha. There's some sense in which this movement is continuous. If we talk about a vector topology on the space of smooth functions here, this gives us a more formal way of explaining that this transformation of this single function is in fact continuous. We can think of vector addition as being a function. I'll call it just the addition sign, right? This is a function. It takes in 2 vectors, x and y, and returns another vector, the sum x plus y. Then we say that addition is continuous if for every x tilde, y tilde, and v, and every open neighborhood u of x tilde plus y tilde, the pre-image of that neighborhood under addition, that's this set, right? This is the set of all vectors such that x plus y is in u. This is an open set in v cross v. So what this is really saying, it's addition is continuous if it's continuous at every vector x plus y. And then this really is just using the definition of f is continuous if for all open u, the pre-image of u is open. That's really all we're doing here. The pre-image set is open in v cross v according to the product topology on v cross v. there exist open sets O1 and O2, both subsets of V, such that the pre-image set here, or this set, can be written as the Cartesian product of O1 cross O2. What this last line is saying is that for all ordered pairs of vectors v and w in O1 cross O2, the vector addition v plus w is contained in U, based off of this last equality. And we can rephrase this in terms of just sets. If we define the sum O1 plus 2 to be all the vectors v plus w, where v is in O1 and w is in O2, then this is saying O1 plus O2 is a subset of U. Let's make sure that makes sense. We have a vector in O1 plus O2. It looks like this. The ordered pair v and w is contained in here, right? Because v is in O1, w is in O2, the ordered pair v and w is contained in here, and we showed earlier this is exactly the set of vectors that satisfies this equality, so immediately follows that O1 plus O2 is contained in V. Here also note that O1 is an open neighborhood of x tilde because x1, x tilde, and y tilde are both in O1 and O2 respectively. So maybe I could add this because x tilde, y tilde is contained in O1 cross O2 because, again, these sets are equal. And then lastly, we'll justify why scalar multiplication is considered a continuous transformation. And we'll represent scalar multiplication using this function from C cross V onto V. C here is your underlying field over which you define your vector space. So it could be C or it could be R. In either case, the proof is exactly the same, as we'll see. This multiplication transformation, it takes a scalar alpha vector x and gives you back alpha times x. We say multiplication is continuous if for all alpha tilde in the complex numbers and x in V. So we have like pointwise continuity. Then all open neighborhoods U of alpha tilde x tilde. The preimage of U under multiplication, that's exactly this set, is open in C cross V. This is true if and only if there exist open neighborhoods O1 in the complex numbers of alpha tilde and O2 in your vector space of x tilde, such that the preimage of U under multiplication is O1 cross O2, and this is by the definition of the product topology. Product topology on C cross V. So we know that alpha tilde is contained in O1, so there exists some positive epsilon such that the epsilon ball around alpha tilde is completely contained in O1. Therefore, for all x in O2 and all complex numbers or scalars beta such that alpha tilde minus beta is less than epsilon, beta times x is contained in U. Well, if alpha tilde minus beta is less than epsilon, that's the same thing as saying beta is in the epsilon neighborhood of alpha tilde, which means beta is contained in O1. That implies that the ordered pair beta and x is contained in O1 cross O2, which we say here is exactly the pre-image, which is exactly the set of scalars and vectors satisfying this. And then lastly, if we define the set beta O2 to be the set of beta of x such that x is in O2, then we can rephrase this as saying that beta O2 is contained in U. So given any vector topology, by definition, this is just really a topology on your vector space, except with the necessary criteria that scalar multiplication here is continuous, as well as vector addition is continuous.